But that's why I use 0.02, a little bit of TFA to improve my peak shape. Those two systems seem to give me my best results.
So you just do 0.02% TFA?
With 0.1% acetic acid. So it's a blended system. The acetic acid improves my protonation, the TFA improves my chromatography. Or you use the second system, which is just 0.1% formic, which does both chromatography and protonation. Those are the two that we've always.
Looks like we need an AMP.
It's an ion pairing reagent. It gets rid of the electrostatic interaction of the peptides with the stationary phase, and it improves your peak shape.
I'll give it one more chance. Have you done any diabetes stuff?
That's what I did my PhD on. On type 2. I was doing type 2, not type 1. So we were looking at glucokinase. In the first step of glycolysis, it transfers the ATP to glucose to make glucose 6-phosphate. And it appears to be the key glucose insulin secretory response. So when insulin needs to be responded, glucokinase interacts with glucokinase regulatory protein and causes the insulin to release. So people with these mutations in GK show type 2 diabetes.
All right, switch it out.
So what people back in the 70s, they were able to take glucokinase with glucose, bind them, and then crystallize and get a crystal structure. And it shows this neat pocket that opens and closes. The problem is no one knows where the ATP binds. The minute you throw the ATP in, the whole thing crashes and it won't crystallize. So we did what I developed a series of ATP analogs that I was trying to covalently bind to show where the, and I got as far. In the end I kind of left it at. I found one analog that generally, no matter what analog I was using, I would add the glucose into the GK, and then I'd put in the analog, and no matter whatever time I let it sit there, I would just start adding analogs onto the GK, non-selectively. The neat one finally was that I developed one analog that when I put it in, no matter what time it was, it instantaneously bound to one spot. Killed the GK activity and never bound anymore. So I thought that was kind of the neat. So when then I did.
So, shall we tune?
How's your injection time?
0.2.
Looks good. Looks nice and stable. Yeah, go for a tune. You already have it open somewhere.
Where are you, Mr. Tune? Check the camera.
Is the audio coming through fine? Cool.
So I used to do automatic. What about the tube lines? What should we do with that?
Oh, auto-tune it. It'll auto-tune for you.
But it doesn't go up to the range.
That's what we'll check. Yep. So hit mass and put in your 433 and hit start. Okay, so now it's tuning the capillary voltage. Okay. Now, what we want to do actually is we're going to retune this one. We're going to up your microscan so we can actually watch these plots. No problem, it'll be done in a sec. Okay, so go to your defined scans, your bubbles. He's going to change his microscans. Onboard signal averaging to 3. Okay, to slow down the scanning. Okay, he's going to redo his tune. Now, first thing we're going to do is we're going to tune the capillary voltage. Do we see a maximum is the question. The blue is the true, the red's the boxcar smoothing. That's a failed tune. We did not see a clear max. Here's your two blends. That's That's a good tune. There's a clear maximum present. Here's your Q00. That's a good tune. We got a clear max. Here's your intermultiple lens 0. That's a good tune. Here's your Q1. That's a good tune. Here's your Q0. That's a good tune. Here's your intermultiple lens 1. That's good. Here's your split lens or gate lens. That's a fail. And here's your front lens. It always dips and then comes back up. So that's a success. So we need to change our capillary and our split gate. So we go to semi-automatic. Okay, make sure your mass says 433. Okay, yep, right there, cool. He picks his capillary voltage and he hits start. Okay, hit OK. And we see if there's a maximum or not.
You just want to expand the range, is that the idea?
Yeah, we got to expand to see a max.
Yeah, this one you typically need to expand it beyond where the semi-automatic is.
Yep. Yep, hit accept. So he's going to take his start lower and his end higher. Then you can take a step size to like a volt or 2 step size. That way the plot goes fast. This now he's going to extend it further. He's going to try to see the maximum.
Yeah,
so here's the rise. Yeah, this is designed for reserpine. Okay. And peptides don't tune anything like reserpine. There we go. Okay, so that one's accept. Okay.
Slightly above the range.
Yeah, just slightly above. And do your split gate. Your gate lens. Yep, hit start and see what it looks like. So accept that and extend your range on each side. Sounds good. And he's not picking, 2 volts is fine. He's not you don't have to pick particular numbers, you just pick larger ranges to see if you find the max. So there's your max.
That was within the range, wasn't it?
Yeah, you just couldn't tell because you couldn't see anything on the plot, so accept it. Okay, hit cancel. Okay. Open up your multipoles.
This one. See if it's sequentially low.
Yep. And then it looks good. 5.5, 6 1/4, 6.5. Q00, multiple 00, multiple 0, and multiple 1.
This one?
Yep. Okay. Cool. You could vary your voltage if you wanted, but this is what you use for your run is 2 kV, right?
Well, I can use whatever is good. I think so.
The key is you would want to vary this with the exact same conditions you're going to run with. Okay. So capillary temperature, you could try 200, 275. It's up to you.
I found it never makes any difference, but so why don't we monitor something?
Monitor the 3 1/4 and the 433 and see what they look like. This is something you do once in your lifetime to see if it makes a difference because it's painfully slow. Okay.
He's getting too far. Get a little screen. Oh yeah. So temperature shouldn't affect charge state distribution, or
It should.
it does.
Yeah. Higher temperature should give you more 433, 649. Lower should give you more 325.